Okay, so here we're going to go over a couple of examples applying the induction principle. Okay, so here, let's start with the hypothesis here, right? What we want to prove. So I want to prove that 1 plus 2 plus 3 to the n, so the sum of the first n terms is n plus 1 over 2, right? In other words, right, I'm proving the sum formula here. The sum of the first n integers is equal to that that formula right there. Okay. Okay. So here again, right, the way you want to approach this is you want to think inductively here, right? Especially here where it's already ordered for us, right? I want to think of a way here. If it's ordered, then I want to use induction, right? So if we know the first k numbers, then adding the next term is k plus 1, right? Then that's easy, right? If I know what the first k terms are, then to add the next one is the k plus 1. So that's kind of the idea here, right? You start with your base case, right? So first of all, let's set up our formal proof here. All right, so P sub n is the statement up here, right? The sum I equals 1 to n is equal to n plus 1 over 2. Okay, so our base case, this one doesn't start at 0, it'll start at 1. So here, let's start by proving the base case, P of 1. Oops. All right, so P of 1, that's just equal to 1, which is 1 plus 1 over 2. So we get 2 times 1, which is 2, over 2, which is 1. So we're done there, right? Base case proven, right? We've shown that the first domino will fall. All right, now let's move on to the next one, right? Now here is the inductive case, right? Here's where the meat of our work is going to come into play, right? The inductive case. All right, so here we assume P of k is true. All right, so what that entails is that the sum of the first k integers will be k plus 1 over 2. Okay. All right. So now from here, I want to prove, so assume here, right? So again, the inductive case is our hypothesis. All right, so from there, I want to prove P sub k plus 1, right? Now that case looks like this, right? So again, let's make sure we use the formulas correctly, right? The next term, according to the formula, would be, remember, we take, this case, k plus 1 is my n, and then my n plus 1 would be k plus 1 plus 1, which is k plus 2 over 2. Right? This is what I need to prove. Right? But I assume this, right? I'm going to use that. Let me not write that arrow there. So I need to prove this quantity here. Okay? That is the inductive test, right? That tells me, right? Inductive case, right? Inductive step, right? And then if that holds for my hypothesis, then it works for every single k. And that proof is done. So this is what we do here, right? So here we start again. We want to show here 1 plus 2 plus 3, etc. K plus k plus 1, right? So I want to show that this leads me to this formula here that I need to prove. Now I need to use my hypothesis somewhere. Well, I'm going to use that one here. Okay. So by my hypothesis, these first k integers follow this formula. All right. So now let me here combine these into one fraction with a common denominator of 2. Now I'm going to avoid multiplying out because I want to actually factor here. All right, so I have this here, and now I'm going to factor out a k plus 1. And now we get the desired formula that we wanted to prove. All right, so now from here we can conclude. So here we did all the proof here was done. So now let's wrap it up, right? Here comes my conclusion here, right? Once we move from here, excuse me, here we said we conclude P of k plus 1 is true. So by induction, P of n holds for all n greater than or equal to 1. Okay. Now I know at first you kind of go through these and it seems like, oh, this doesn't seem like a proof, but this works, right? Again, think of those dominoes, right? That k represents any integer along the way. So it represents 1, that means that 2 falls, that 2 would be true. If it represents 2, that means 3 will be true, right? If it represents 3, that means 4 will be true, etc., right? That's why once you establish that base case, that it works, right, then the next one, right, is just a general k, right? And if you show that that makes the next domino fall, then it's going to work for all values of n. All right? So it's a really powerful technique, right? As long as what we're out to prove lends itself to induction, right? Which not all statements will, right? These work for particular formulas that we're out to prove. All right, let's try one more here. All right, so here we're out to prove that 6 to the n minus 1 is a multiple of 5 for all n element of the natural numbers. Okay, again, natural numbers being the numbers from 0, 1, 2, 3, etc., right? So all non-negative integers, essentially. Okay, all right, so again, right, when thinking of proving this, I say, okay, see a formula involving some nth term here, so I want to think inductively, right? What does it mean to go from the k term to the k plus 1, right? That's including another factor of 6. Okay, so again, let's formalize our proof here. All right. So our proof here, we'll start with the base case, right? Or actually, sorry, take a step back. We'll start with what we're proving, right? What's our P of n? P of n is that 6 to the n minus 1 is a multiple of 5. That is this for j being some integer. Okay? Okay. All right, so here we've defined what P of n is. So now let's do our base case. P of 0. All right, so that equals to 6 to the 0 minus 1, which is 1 minus 1, which is equal to 0. But 0 can be written as 0 times 5. So here we have a multiple of 5. So true for the base case. Okay? All right. So now let's look at our inductive case. All right, so we assume P sub k is true. So what that means is 6 to the k minus 1 is equal to 5. We're not letters. 5j for, actually, yeah, 5j for some j element of z. Okay, so this is my hypothesis. Okay, so now let's go and here try to prove the k plus 1. So P sub k plus 1, all right, so that is going to look like this, right? So 6 to the k plus 1 minus 1, and I need to show that this is equal to 5m. Right, this is my conclusion. All right, got an implication, hypothesis, all right, conclusion, 5 times m, where again m is an integer. All right, I need to prove this, right? I'm not assuming this, right? I assume the above, the k case. So here, let's start with 6 to the k plus 1 minus 6. So this equals to, again, powers of x, or excuse me, properties of exponents. I could write like this. All right, and now here is where I bring in my inductive case. Right, previously we have, okay, well, I know what this is equal to, right? By my hypothesis, 6 to the k, excuse me. Okay, 6 to the k plus 1. Okay, all right. Okay, so here is, going to use a little mathematical trick here. So actually here, since actually what I am going to do here is I'm going to use my hypothesis, and here I know that 6 to the k minus 1 is equal to 5j. So 6 to the k is 5j plus 1, right? Adding 1 to both sides. So again, right, I'm assuming this is true, right? That's my hypothesis, so I can treat it like an equation here. So here we have 5j plus 1 minus 1 here, and doing this here, we get 30j plus 6 minus 1 equals to 30j plus 5. And now I can factor out of 5, and we get 6j plus 5. And here we let m equal to 6j plus 5. M is some integer, since we have a product of two integers, and then we add another integer, 5m. And now we have our desired result, right? P of k plus 1 is true. All right, so our inductive case is true. So what we can say, therefore, by induction, P of n is true for all n, element of n, right, for all natural numbers.